I'm going to talk about what have been called in the past dirty fireballs, perhaps somewhat unfortunately named cosmic event. I would discourage you from sort of doing a Google image search for dirty fireballs. Really the best thing you will get is this cinnamon whiskey called Fireball. So instead I put up a picture here. This is Dale's favorite rock and roll band called Afterglow Radio. They are well known in Central Florida for being up and coming. So I think it's important here to sort of take a step back and ask, why do we really care about gamma ray bursts? The answer that I'm going to give to that talk is because they are really the most relativistic explosions that we know of in the universe. So there are a variety of different systems, astrophysical systems that can generate jets, even all the way down. We have these beautiful pictures. Do we have another pointer? Sorry, this one's kind of, oh, it looks okay here. Oh, in front of me, okay. Perfect, thank you. Are capable of generating jets. We have these really nice pictures from HST of even in young stellar objects that can achieve velocities of a few hundred kilometers a second. There are only a small handful of systems that can generate relativistic ejecta. In microquasars, stellar mass black holes, accreting material, you see these sort of superluminal outflows in our galaxy and suggesting Lorentz factors of order of a few. In blazars at higher redshift, we see these jets. This is actually a resolved HST image of 3C279, where we can get Lorentz factors of, let's say, of order up to about 10. And relatively recent addition to this class, the tidal disruption events, where we have evidence, again, sort of Lorentz factors of order of a few to 10 following the shredding of a star by a supermassive black hole. This is exactly what the accelerating universe should mean, Bob. I'm glad you picked up on that. Thank you. So GRBs are really, you've seen this cartoon a couple times before, the most relativistic sources that we know about. Instead of Lorentz factors of a few, maybe up to 10. We heard from Rem that we require Lorentz factors of order 100, maybe in some cases up to 1,000 from this compactness argument. And in one case, we've actually measured the angular size. This is the same plot Rem showed earlier from GRB 030329, where we can measure the angular extent of this GRB and see that it is expanding with inferred relativistic speeds. But if you do, in order to get to this ultra-relativistic expansion, the jet that's coming out of the system has to be relatively clean. I would say actually relatively fine-tuned baryon content in the jet to generate what we sort of in our standard picture, at least which we teach our students, is a GRB. If there is too small of a baryon content in this jet moving out from the system, we're not going to get these internal shocks, right? We're not going to see different shells with different speeds colliding with each other and giving us the significant amount of energy in gamma rays that we call a GRB. On the other hand, if there's too much baryon content in this jet, there's not enough energy to accelerate it up to these speeds and to give us peak energies that we observe at a few hundred keV. So this is a distribution of swift GRBs, the peak energy observed in the prompt spectrum from some work that Nat Butler did. And again, Rem alluded to this briefly. It's relatively narrowly collimated around a few hundred keV. But one thing that a number of models have shown, both from observations with HEDI and simulations of detector sensitivities and thresholding, suggests that there might be a pretty large population of events down here at low energies. We used to call these X-ray flashes. This is something that seems to have gone out of fashion for a number of reasons. But perhaps one explanation for what is causing these X-ray flashes, and there are certainly other ones, is that you have a GRB-like jet with a large baryon loading. Instead of like 10 to the 5 solar masses, this jet is plowing through this extended envelope of this massive star. It's not crazy to think that you might pick up or entrain a larger amount of baryons as it goes out. That would lead to a smaller initial Lorentz factor, and so a smaller sort of peak energy in the spectrum. And we call these things traditionally, like I said, dirty fireballs. Okay, a separate but related picture, also alluded to both in our previous talks, is the issue of collimation and jet brakes. So we now have, I think everyone sort of believes that GRBs are highly collimated explosions, opening angles, at least in the case of long duration GRBs, of order a few, maybe 10 degrees. But the strongest supporting evidence we still have comes from these achromatic jet brakes. And it's kind of, you know, embarrassing that it's, I think, to people in our field that we've been inferring the fact that we have these very collimated explosions, only 1 of 100 are actually pointed along our site, but we still have no really good evidence for what we call orphan afterglows. Those are events where the jet is not initially pointed along our site, but eventually it spreads in and we see rising emission from that. And so there's been a good amount of effort in the past decade plus, but like I said, pretty much every candidate that has been detected has sort of later been debunked as a flaring AGN, blazar of some kind, maybe a low mass star that just goes into outburst. And we really haven't seen anything that looks like this classical picture of an off-axis GRB, where instead of this rapidly fading emission that then decays more steeply after the jet break, we see this sort of slowly rising emission until the jet spreads into the observer's line of sight, and then it joins more or less what you might expect for the post-jet break decay. So we have been looking for relativistic explosions independent of high energy triggers with a variety of different systems. And I'll talk briefly about some of the results we've gotten here from the Palomar Transient Factory. To remind you, since I think most people are pretty familiar, the idea of PTF is to have this sort of integrated system where we have a wide field search on the Palomar 48-inch Schmidt telescope, 7 square degree field of view, tightly coupled with multicolor follow-up from the 60-inch telescope at Palomar and other facilities, and also with an integrated spectroscopy program from the 200-inch Keck Gemini Discovery Channel telescope, this sort of inverted pyramid picture. And I'm going to talk about 2 approaches. The first is looking for what I'll call fast optical transients, where you can define that somewhat arbitrarily as a change in magnitude of, let's say, more than half in a time scale of an hour or a couple of hours. These are something that you definitely do not see even in sort of the very earliest rises, like from supernovae, and so are pretty characteristic, at least at large distances, of relativistic explosions. And the other, looking for off-axis events. I'll talk about a campaign that's been led by Alessandro Corsi to do radio and X-ray follow-up of nearby type 1c broad-line supernovae. So what have we found thus far looking for these fast extragalactic luminous transients? The probably most interesting discovery, I would say, at least with the follow-up data that we have, is this source iPTF 14YB. The name tells you from February of 2014. The first image was taken at about 9 o'clock UT. There's nothing at this location. About an hour later, we got a second image, 18th magnitude transient. Come back 2 hours later, it had faded by 2.5 magnitudes. And just to give you a sense, this is our reference image here. Show you that there's really nothing at this location. So this actually does not happen entirely infrequently. You do see these kinds of dramatic flares, in particular from low mass stars. And so if you want to be able to pick out the relatively rare extragalactic transient from the more common low mass star outbursts, you really need to identify these things quickly and trigger multi-wavelength follow-up. So I think sort of the technical aspect of this is what I think is most impressive. So within a time scale of a couple of hours after discovery, we were able to obtain additional imaging and a spectrum, trigger SWIFT and the VLA for follow-up, and that's where we were able to show that this source continued to fade over a time scale of a day, like a power law in time, bright X-ray emission. This is some Grand data. I saw Jochen in the audience back there showing a power law spectrum, all very much like on-axis GRBs. But most importantly, we're able to get a spectrum. This is where you actually are able to really effectively classify and gain physical insight into the source. You see this power law continuum superposed with narrow absorption features, Lyman alpha, and a number of other ones indicating a redshift of 2. So this is the most luminous transient we've discovered from iPTF to date. If you take its 18th magnitude discovery image, put it at a redshift 2 minus 28th magnitude. So for those of you who are superluminous supernova folks, this kind of, I think, you know, it's pretty amazing how much energy is coming out with these things. And so we were really excited by this. There were no reports of corresponding gamma ray bursts initially. So we thought, you know, this was the first time that we might have a real bona fide orphan GRB afterglow. Unfortunately, or, you know, I guess perhaps less, less interesting, but, you know, confirming that this is actually what we saw, the parent GRB was subsequently identified by the Interplanetary Network. So it turned out that the Fermi Gamma Ray Burst Monitor, which sees a large area of the sky, was actually in the South Atlantic anomaly at this time. SWIFT was looking at a different direction, but this all-sky IPN, which is not as sensitive as those other facilities, but can see sort of all the sky, was able to pick out this gamma ray burst that was at a time window that was sort of within that 1 hour gap where we knew the event went off, and at a spatial position that was coincidence with this event. So the probability of chance coincidence is very small, and we say very likely this is, you know, the parent GRB of this event. And so iPTF 14YB was essentially a normal on-axis GRB afterglow that we just identified in a completely novel way. So, you know, I actually, after we published the paper on this, I got a couple of queries from some reporters, and I was a little surprised. We didn't put out like a press release or anything. I was told as a NASA employee it was probably not a good idea to put out a press release saying we no longer need high energy emissions to detect GRBs. But nonetheless, I got a couple queries and I was really straight. I thought this is kind of strange. You know, our reporter's starting to read the archive, what's going on here? And instead it turned out that Bob, if you've ever followed, Bob Rutledge has a large number of Twitter follows and posted something about this, suggesting that this was the 5th era, the triggerless afterglow era, heralded by the discovery of this object. It's been somewhat of a, I'd say, maybe not quite that exciting of an era yet, since this tweet actually has more reposts than the paper has citations that it was discovered. But that's okay because, you know, we're modern people. This is how we judge our scientific productivity is on Twitter now. So great. Okay. There's one other discovery that I want to talk about that I think is sort of very interesting in this dirty fireball context because I think it's still a candidate and one of the few remaining candidates that we have out there. And this was from 2011, so it was discovered before iPTF 14YB. Again, very bright transient, faded by 1.5 magnitudes in 5 hours, 4 magnitudes in 2 days. The light curve here is shown in black. Unfortunately, we don't have great constraints on the previous non-detections. We only have a 1 or 2 day window when the explosion time could have gone off, so you can imagine shifting this by some amount. But in general, the sort of rapid decay over a time scale of a couple days is very typical of what this is a sort of unbiased sample of optical afterglows of GRBs. And at this location, we looked very sensitively to see, do we see any sort of faint, low mass potential stars near infrared? There was a very faint 26 magnitude blue object at this location in the optical bandpass that looks marginally extended like a galaxy. Wouldn't say conclusively, but possibly extended. What was sort of really interesting about this source, in addition to the optical, is that we were able to get radio follow-up. Not right away, because we didn't have all the sort of real-time tools that we had in 2014, but on a longer time scale of a few weeks. But fortunately, the radio emission from relativistic explosions evolves on a longer time scale, and there was a relatively bright radio counterpart. It continued to fade for, this is 100 days right here, so we're able actually to track it over the course of a year. And you can see that it's kind of bouncing up around this sort of general secular trend. And this looks very much like, if you remember the slide that Rem showed at the beginning, the scintillation, where there's variability due to scintillation by gas along the line of sight from in our galaxy. And using that, you can get a rough estimate of the angular size, the degree of scintillation about this secular trend. And this tells us that this source had a size of about 20 milliarcseconds at a time scale of about a month after the burst. And so for any reasonable cosmological distance, this requires moderately relativistic ejecta, Lorentz factor of a few. There is no high energy counterpart to this source, not from the IPN or any of the other detectors, Because of the relatively wide window in which we have for which it could have gone off, I would say this is not, from Swift and Fermi, it's not extremely constraining. But again, the majority of events that have bright optical afterglows are detected by the IPN. One other thing I'll say is that this is not consistent with off-axis afterglow models. The relatively rapid decay in the optical that we saw from very early times, coupled with this longer-lived radio afterglow, does not fit sort of our picture of any sort of realistic off-axis afterglow models. So we think whatever this thing is we're almost certainly viewing it on axis. But whether it is actually a dirty fireball or not, I'd say it's still, unfortunately, something I don't know if we'll ever know until we get a larger sample of them. So we can go through and actually calculate what are the rates of these fast optical transients. So this is a volumetric rate, assuming everything looks like either PTF11 AGG or iPTF 14YB. As a function of survey time scale, where we take roughly an hour as sort of the typical iPTF limit. And you can see that comparing to, say, the sort of rate of on-axis Swift GRBs with large uncertainty, these two events that we have are roughly consistent with the on-axis GRB rate. So there is not a large population of bright, fast-fading, on-axis relativistic explosions, dirty fireball-like things, which had been hinted at by previous studies, but we're really able to pin down now with iPTF. You know, for the first time, we're actually able to be sensitive to these kind of limits. Okay, switching gears to, how much time do I have left, Dito? Sorry. Okay, perfect. To orphan afterglow searches. For off-axis events, we really can't rely on looking for these very bright, fast-fading counterparts. So this is, I showed a few sample light curves before. These are some updated ones for an event that's viewed directly on axis, sort of slightly off axis, and then at larger viewing angles. And for comparison, this is the light curve of supernova 1998 BW. And what you'll notice is that for the majority of times, and for the majority of viewing angles, right, most viewing angles are relatively far off axis, the supernova emission is actually brighter than the off-axis optical afterglow emission. It's from a paper that was on the archive recently, Dimitrios Giannios' group. So instead of looking for these sort of fast-lived transients that I was talking about before, what we've been doing is targeted radio and X-ray follow-up of all the Broad-Lined SNe supernovae that have been discovered by iPTF. This is work that, like I said, was led by Alessandro Corsi. There are a number of efforts, many of them led by people just up the road doing something similar. But what we've tried to do is really focus on these Broad-Lined SNe type supernovae in the unbiased sample that iPTF gives you. We already know that there are a continuum of explosion properties from ordinary type 1bc supernovae to subenergetic GRBs. Rem was alluding to this briefly, to full-fledged relativistic outflows. I think we'll see a plot like this later in the core collapse session. And this is showing the kinetic energy of the explosion compared to the ejecta velocity. For pure hydrodynamic explosions, like most type 1bc supernovae, you expect something to go like gamma beta to the -5 power. Not a lot of energy coupled to the very fastest moving ejecta. GRBs are able to couple a tremendous amount of energy to the fastest moving ejecta. And there's a growing population of events that are sort of in between, either identified by their prompt emission or identified first by their supernova, and then by looking at sort of multi-wavelength observations to pin down how much energy is coupled to this fastest moving ejecta. So we have a sample of 15 Broad-Lined type 1c supernovae, all at redshifts around 0.1. This is just showing their optical spectra around max, showing that in general they're pretty good matches either to supernova 1998 BW or supernova 2009 BB or supernova 2003 JD or any of these other events that we call sort of Broad-Lined type 1c supernovae, lacking both hydrogen and helium in their spectra. These are the radio limits. So this is radioluminosity, isotropic radioluminosity as a function of time after discovery. For the 12 events for which there are no detections, are shown. Our work limits are shown in black, and limits that other people have placed are shown in the yellow here. And you can see that for almost all these events, we can rule out anything like supernova 98 BW. So any of these very isotropic explosions with a good amount of energy coupled to ejecta with a Lorentz factor of order of few, we're showing that the vast majority of type broadline 1C supernovae don't have these kind of outflows, okay? And the limits we place, I think, are something like, 14%, just based on this. There are several of events that show radio detections. The peak time scale of this radio emission is significantly longer than supernova 98 BW. So this implies either that we're seeing something moving with lower velocity instead of sort of trans-relativistic outflows, maybe something like 0.3 C into a dense and complex circumstellar medium. Or we're looking at an off-axis GRB, but it still requires a reasonably dense circumstellar medium. It's actually relatively hard to distinguish between these kind of two pictures of what's going on. Certainly the lower velocity dense CSM is the sort of simpler, and I would say we see this in other events, other type 1BC that don't necessarily have broad lines, so I think that's the simplest explanation. But it's very hard to rule out off-axis GRBs, particularly for events that have relatively low density circumburst media. Okay, so I think I'm gonna just finish up there, repeat sort of summary and conclusions. For the first time, we're detecting relativistic explosions independent of high energy triggers with surveys like the Palomar Transient Factory. I think with new surveys coming online, we're gonna have a session on surveys in a couple of days. The prospects for doing this are going to get significantly better. We can already say that the rate of dirty fireballs is at most comparable to the rate of on-axis afterglows. The X-ray and radio follow-up we have from broadline type 1C supernovae constrain that these 98 BW-like explosions, at least among the broadline 1C population, are relatively rare. And several events, on the other hand, show evidence for this late-time radio emission, and distinguishing between a dense CSM and off-axis GRB is challenging. So I'll finish there and take any questions.
I actually have two questions. One about the last point you made. So you mentioned that it's really hard to distinguish, which actually would be very surprising. For example, 11 CGQ, I think you showed that it has a plateau and it goes up again. Would that ever be able to be explained by an off-axis radio light curve?
So let's see. It's hard to get sort of, if you imagine that this is a second peak and it continues to rise at these times, then yes, that's extremely difficult to get with an off-axis light curve. If you just try and fit it with something that sort of comes up and captures most of this and then comes down afterwards, you can do reasonably well. But this is something, that we've been observing since 2011, so 5 years now. And if you want to know, is this going to continue to rise or is it going to decline, you'd have to monitor it for a pretty long period of time. So you're not going to get a chi-squared equals 1 fit to something like this, but you can broadly match, and it's hard to, I would say it's hard to get a chi-squared equals 1 fit even to sort of a strange density profile for something like this. Those models are pretty simple and not perfect for that.
So my second question is about iPTF 14YB. So you mentioned that it's actually very hard to distinguish it from flaring stars and so forth, but how were you guys able to do it and to trigger all the follow-up, and especially since it doesn't have a host galaxy? Oh, it doesn't have a host galaxy, right? So you couldn't know that it was something cosmological and not just a flaring star in a Milky Way. Or are you allowed to talk about it? Or?
Sure, I'll give two answers to that. One is we have some spectra of flaring M stars. If there's anyone who's actually interested in those, I don't think we are extremely so. The other answer is, we have reasonable past history at a number of these locations. So we can say, have we seen any flares in the past? We have contextual information, and we've put a lot of time and effort into building up an infrastructure to be able to make decisions like that on a reasonably fast time scale. So does that answer your question to some extent?
Well, what is your false alarm rate?
False alarm rate in terms of fast transients? I would say, you know, we have one event and we have maybe of order 10 to tens of spectra of things that are, you know, dwarf nova outbursts or M-dwarf star flares.